In this video, we're going to talk about the momentum principle again. We'll kind of wrap that up. We'll move into energy and what it is. And we'll talk about some of the forms that it can take and some of the energy resources that we can get in society to convert to more useful types. And we'll talk about the energy principle, which is our next principle to discuss, and another tool to solve problems. And so we'll apply that to a problem here where we have the same force acting on two different masses. And we know that, for example, with a semi-truck and a car, when you have a bigger mass, it's going to be harder to accelerate with the same force. Okay, so covering the momentum principle again, remember we have momentum, which is mass times velocity, and we have, anytime we have a change in that momentum, we have impulse, and both of them are vectors, and they have direction, right? And so we a lot of times make the assumption that the net force is pretty much constant, and there's a small enough time interval. We can do these updates, right? And so that's where we get our momentum principle from. It basically comes from Newton's second law, and it connects this idea of the change in momentum to a force or acting over a certain time interval. And so we have a change in momentum set up there. And then we can update our position if we know information about our momentum change. So a lot of times we can approximate by just taking, hey, we'll solve for our final momentum and we'll plug it in, and we can get our final position as long as we know our initial position pretty much. And so that gives you a review of the momentum principle. But now we're going to get into energy. And so how do you define it? Well, one way to do it is just saying energy is the ability to do work, or more generally cause change. Another way to think about it is that it's a property that can be transferred to different objects or transformed into different types. And another thing to keep in mind is that we can measure energy, right? And so we can measure it in joules or Newton meters. It's a quantity. And so we look on the nutrition facts of drinks and food, and we see calories, right? We can measure energy content in food. We can look at electron volts or even British thermal units, BTU. Another thing to keep in mind when you talk about energy is that it's very similar to mass, right? So that you have this energy mass equivalence from Einstein, and he basically was saying that the energy of a particle is this gamma term, which is for relativistic speeds, times the rest energy. And so if you look at just the rest energy, you basically get mc squared. And so when you're at non-relativistic speeds. And so what this is telling us is that we have an equation that relates energy is equal to mass. You just got to multiply by the speed of light squared. And so one way to think about this is if you have two protons and two neutrons coming together, if you look at the atomic mass units here in terms of the mass here of these four things separately, we can look at what a helium nucleus would be, and we see how it's just a little bit less than that. And so there's some sort of energy here that was associated with that as well. And so it doesn't seem like a lot, but we do have to account for matter and energy, especially at the smallest levels. And so the other thing to think about is how to classify energy. Energy is such a big concept, so we got to basically break it up into categories. And so a lot of times what we do is we say, okay, there's two types of energy, right? There's potential energy, which is a result of position or state, and we notate that as PE, U, V, or I like to use capital E, lowercase p, like as a subscript, similar to forces. Anytime you have a force, you have a capital F and a subscript what the type is. Anytime you have energy, you got a capital E. And so I've been trying to use that as my notation, but you can use different notations for sure. And then there's different types of potential energy. And so you can have gravitational potential energy, dependent on masses, right? And the gravitational force, it's similar to, right? And then we have elastic potential energy, which is having to do pretty much with springs, very similar to that Hooke's law idea. And we have electric potential energy, where we pretty much have Coulomb's law, but it has to do with the potential energy of electric charges. And we have formulas associated with these. But the other basic type is kinetic energy, right? And so if it's not due to position or state, it's due to motion. And so a very common one is this formula, 1/2 mv squared. And we can notate this with Ke, K, or Ek. And so that's how we can break energy down into two basic types. The other thing we can do is look at basic forms of energy. And so a lot of times we're dealing with just mechanical energy. And so we can say, okay, all energy is either mechanical or non-mechanical. And then we can break it up into kinetic or potential. And then potential a lot of times is just gravitational or elastic. That solves a lot of problems in physics, but there's a lot of other ways to classify energy and a lot of other things that can happen. And so we could look at sound energy, where we have this energy propagating through space as a pressure wave through a medium. We have thermal energy, which is basically the potential and kinetic energy of all the microscopic particles in an object. And when it moves faster, the thermal energy increases and it becomes warmer, right? We have electrical energy associated with electric charges and electric fields. We have magnetic energy, which can be thought of as the potential energy stored in magnetic fields, like with inductors. We can think about radiant energy or electromagnetic radiation, so light energy, or nuclear radiation traveling in the form of waves or particles, such as like sunlight or alpha particles. We have chemical energy, which is associated with chemical bonds with chemistry, for example. And so we have when bonds are formed, energy is released. So a lot of times when bonds form, they do that because they're trying to get to a more stable state. So they're releasing energy to be at a lesser energy and more stable. And so we have all chemical compounds storing energy, like, for example, fuels. You can think about gas, food. And we have nuclear energy. And so we have energy stored in atomic nuclei. And we could think about nuclear fission and nuclear fusion with that, with the nucleus of an atom. And so those are some of the common forms to think about with energy. So now we get into energy resources. So energy resources are important for society because energy exists in all these different forms, and a lot of times we want electricity, for example. And so how do we take some of the less useful energy resources in society and convert them into more useful ones? And so we basically have renewable energy resources, and they can be replaced in a short period of time. And so we have biomass, hydropower, geothermal, wind, and solar. And we also have non-renewable, and so it takes a long time to form naturally. And so, for example, fossil fuels, you have decayed plants and animals that are converted into crude oil over a long period of time with exposure to heat and pressure. And so we have petroleum as an example, natural gas, coal, uranium, propane. And so we would consider these non-renewable. It doesn't mean that they can't be renewed at all. It just means it takes a long time, and it's not as practical to renew. And so with that in mind, as a society, we continue to consume more and more energy. And so we want to be mindful of that, and we want to be mindful of conserving these energy resources. And the basic idea is that hopefully we're going to have less need and more efficiency, at least on an individual level, right? So what you could do is reduce what you use and rethink your needs. You can reuse and repair things, and then you can recycle or at least properly dispose of things. And so that's three things to keep in mind when it comes to conserving energy resources. All right, so now we get into the energy principle. So you got a little bit of background on what energy is all about. So the energy principle is basically this idea that this concept of energy is conserved throughout the whole universe. It's a constant, right? And so the energy cannot be created or destroyed. And it can only be transformed, so converted into a different type, or transferred, so moved into a different object. And the way in which energy can be transferred, the mechanisms, we usually talk about heat and work, all right? And so what we could do is basically draw the biggest system that we can draw, which is the whole universe, just to try to understand these concepts. And so we're saying that within this universe, there's some sort of an energy, the energy of the universe, which could be composed of the system and the surroundings, right? And that's constant. And if it's constant, we don't need to know what it is. If it is a constant, then we are going to say, okay, well, the change in energy in the universe is zero. So the energy in the universe is not changing. And that's a fundamental assumption. So when we do that, we can say, okay, well, if there's going to be a change in energy of my system, then it must be going to my surroundings, and vice versa. So whatever is lost by one is gained by the other, for example. All right, and so we take this idea and then we say, okay, well, there's a system and surroundings, right? And so we could do the same thing for a system, but in this case, it's not necessarily constant, right? So we said that there could be some energy flowing into and out of the system, but we're asking ourselves, hey, there's an energy associated with this system. Is it constant? And so a lot of times we're like, okay, well, that's composed of kinetic and potential energy as our two types. And so if there is a change, it must be coming from a change in kinetic or a change in potential, right? Is that zero? So this only really happens for an isolated system. And so we're asking the question, is the change in kinetic energy equal to the negative change in potential? It doesn't always happen, but those are the things that we can ask about the system, right? And so when we have energy changes in our system, we basically have two ways to do that, right? So one of them is work. And so we either have work being done, on the system by the surroundings, or we have work being done on the surroundings by the system. And so a lot of times what we do is we define this so that a positive amount of work is adding energy to the system. Okay, so when I plug in a positive number for W, I'm getting more energy in my system. It's kind of like a system-centered definition. And so that's the way that this notation is set up. But whatever is going into my system is the negative of what's leaving the surroundings, pretty much. So the work done in the surroundings is equal to the negative work done in the system. And so we have this idea of work, and so we have work can be done by forces. So we can integrate if it's a non-constant force, but the idea is that we have this dot product between force and some sort of a displacement. And so when we do a dot product, we get to a scalar. So we go from a vector that has direction to a scalar. And we know energy is a scalar quantity, so we basically are removing the direction here, and we get this integral here. And a lot of times we can move the f and the cosine theta outside as long as the force is constant. And we can say, okay, well, work is basically force times displacement, and times the cosine of the angle between the two things for a constant force. That's one way to get work. Another way to think about it is with the work kinetic energy theorem. And so there's really three ways to get to this. One is from Newton's second law. So we have the net force equals ma, right? And so we can multiply both sides by v. We can plug in dx over dt for this v, and we can basically rearrange, and we can integrate both sides, and we end up with this idea of this 1/2 mv squared final minus 1/2 mv squared initial, which, if you remember, that's the formula for kinetic energy. So that's some sort of a change in kinetic energy is equal to some sort of a force times displacement. So the idea is that we have some sort of a net work being done. It would be equal to a change in kinetic energy. So it's called the work kinetic energy theorem. Another way to think about it is with a kinematic equation. And so we have one of the kinematic equations here that does not have time in it. And so we are going to solve that for the displacement, and then we can plug it into this net work equals the net force times the displacement. And so when we plug that in there, we end up with a nice formula here for, we also plug in MA for the F net, and we end up basically with the same result, right? So it's another way to get to the same thing. We also have internal and surrounding work, right? And so what we could do is say, okay, well, work from the surroundings on the system is going to result in a change in energy of the system, right? Which is going to be a change in kinetic energy plus a change in potential. And we also have this idea that any internal work done by internal forces of the system is negative change in potential energy. And so when we set that up and we add them together, we get this net work. And so the work done by internal forces plus the work done from the surroundings is going to be the change in kinetic energy. You can kind of see here the change in kinetic plus change in potential minus change in potential. You're just left with the change in kinetic. And so again, we have change in kinetic energy equals the net work. And so that's the work kinetic energy theorem. Now, the other way is by heat. To change energy of your system, right? And so again, we have a positive amount of Q for heat is going to add energy to the system. And so Q surroundings is, again, just negative Q system. It's just the way that we define it. And we end up with this idea of heat where we can, for example, find heat by saying, okay, well, if there was a change in temperature, we have a mass that's changing temperature. We have the specific heat capacity of that thing that's changing temperature. Let's say it's copper. And then we have some sort of a change in temperature. And so we can calculate what sort of heat was transferred there. And we can also look at phase changes. So looking at the latent heat of fusion or vaporization. So, for example, when water freezes or when ice melts, there's some sort of an energy associated with that, and there's some sort of heat that had to happen. And so that's another way to look at the heat formula. So we combine these two ideas together, work and heat, as the two main mechanisms for changing the energy of my system. And I end up getting this idea of pretty much the first law of thermodynamics. And we end up saying, okay, well, if there's going to be a change in energy of my system, it's going to be coming from Q surroundings or it's going to be coming from work surroundings. And so, and remember, when I plug in positive values to each of these, it's going to result in a adding of energy to the system. That's the main idea here with how we defined it. And what the other thing that you can think about is that if you have a system, like let's say it's a heat engine, the work that you put in is not always going to be equal to the work that you get out, right? So it comes into this idea of efficiency. So whatever energy you put in is going to be greater than or equal to what you get out. For example, a Carnot engine is like this theoretical most efficient engine that you can get. And even without friction, and if everything's running perfectly, you're still not going to get as much energy out as you put in because you got heat loss, right? So unless you're converting 100% of it to useful work, we're going to have some sort of losses, right? And so that's this idea of work in equals work out, or work in is greater than work out. And that solves a lot of problems with simple machines and things like that too. So the other thing to think about is a lot of times we say, okay, well, if there's going to be a change in energy of our system, I don't really care about Q. So a lot of times we're not looking at Q, we're just looking at work. And so we can just say change in energy of the system is equal to the work surroundings, right? If that's the case. And if that's the case, we can then end up with this formula here if we're not considering heat. And we end up saying, okay, well, change in energy of the system is change in kinetic energy plus change in potential energy, which is the work from the surroundings. And so that really is what the energy principle is all about. It's about looking at the system and the surroundings, the energy flowing into and out, the two mechanisms that are doing that, which is work and heat, and basically accounting for that, right? Accounting for any energy changes to the system, assuming that the energy in the universe is constant. That kind of is like the fundamental assumption. All right, and so now we get to our problem. In this problem, we have two different masses, right? So one of them's mass m, one of them's mass 4m, traveling a distance L to a finish line, right? They're experiencing the same force. And for part one, we're asked to read what this student says and figure out whether or not we agree. And so when asked which disk has more momentum when it crosses the finish line, one of the students says the less massive disk is going to be moving faster when it crosses the finish line. So that's a good assumption, right? Because if it's experiencing the same force, it's going to be easier to accelerate a lower mass, right? And so we are going to have a higher velocity at the finish line. Let's keep reading though. The faster speed compensates for the lower mass. So each disk has the same momentum as it crosses the finish line. And so the student's arguing, okay, well, the mass is going to compensate. Even though the lower mass is going to be traveling faster and the higher mass is going to be traveling slower, those things are going to cancel out when you do mass times velocity for momentum, and they're going to have the same momentum when they cross the finish line. However, we can't really agree with that second part, and here's why. So we're going to have to disagree with this statement. And we can agree with the first part where we say, okay, well, the speed of the less massive disk is going to be greater, right, when it crosses the finish line. That's okay. But we have to consider that it's the same exact force acting on two different masses. And it's going to take the bigger mass longer. And so we're saying, okay, well, this force is acting for a longer period of time. And when we look at the momentum principle, remember, the change in momentum is equal to the force times the time. So it's going to be the same force acting for a longer period of time. And so that tells us that the momentum of the more massive disk is actually going to be larger when it crosses the finish line. So there's a little bit of an issue with the students' thinking there. The next part is looking at, hey, can we figure out the speed of each disk as it crosses the finish line? Now, I don't have numbers, but can we come up with an expression? And so we'll identify our system as each disk, right, separately pretty much. And then we have the surroundings which are affecting these disks. So we have an applied force, which is constant to the right. We have the earth with the gravitational force. We got the ground providing some sort of a normal force, right? We have the momentum principle that we're going to use here. And we're going to make some assumptions that the ice is very smooth, because it says very smooth, right? And so there's no friction that we have to consider, no aerodynamic friction. We're going to assume that the velocity is much, much less than the speed of light. And so when we solve this problem, we're going to use the momentum principle here. The final momentum equals the initial momentum plus whatever this net force is times the time interval in which that force is acting. We're also going to use the idea of average velocity is displacement over time. And when that force is constant, we can say it's just half of the initial plus the final velocity. And so those are the two ideas we're going to use here to solve for the final velocity. What we can do is use the average velocity formula here. We'll use this part of it. And we will say, okay, well, the initial velocity is 0 because it says it starts at rest. So we can kind of cross that out immediately. We can then rearrange here and we can solve for time. Now, the reason why we're solving for time is we would love to use this formula here, right? But we can't, because we don't really know what time is. Like, we're asked to solve for the final velocity, which has to do with the final momentum, but we also don't know the time. And so when we have two unknowns, we need two equations, right? And so that's why we have two equations. We're basically solving the one equation for time, and we're going to substitute it into the other one to get rid of time, because I don't care about time. It never really asked us about how much time it took. We don't really care about it, so I need an expression that represents time that is not actually time. And so we're going to take that, we'll plug it in over here. We don't have any initial momentum. We'll plug it in here. So we got 2L over VF. We also recognize that the final momentum is mass times the final velocity. And so now I have the variable I'm trying to solve for, which is final velocity. I need to get them together. And so when we do that, we multiply up and we get VF squared. We're going to have to take a square root. And so we get the square root of 2FL over M. All right. And so that is just generically how we would solve the problem, but we have to apply it to each mass. And so we get this idea that the final velocity of this first M, right, we would just plug in big M for this M here, and we know it's going to be faster and less massive. And then we get the final velocity of the bigger mass, the 4M. We can plug in that 4M down there. And we know that that's going to be slower and more massive, okay? So that's how we would get expressions for the final velocities using the momentum principle, all right? So now let's start to think a little bit more about energy. And so let's look at another statement. So when asked which disk has more kinetic energy when it crosses the finish line. One student said the less massive disk is moving faster when it crosses the finish line. Okay, well, we kind of already agreed with that. Since the kinetic energy depends on the speed squared, because remember it's 1/2 mv squared, that more than compensates for the disk's lower mass. So it has more kinetic energy than the more massive one. So we definitely want to analyze that second part, right? And so do we agree or do we not agree? And so in this case, we're going to disagree. So we have a net force acting on each disk. It's going to be the same, right? And then we have the same distance as well. So we have the same force over the same distance. And the energy principle says, remember, that if you have a change in energy of the system, as long as we're not including heat, it's just basically equal to the work done by the surroundings. And so if we travel the same, if we have the same force acting the same distance, their energies are going to be the same, right? So remember, work is basically force times distance. So we have the same force, same distance. It's going to be the same kinetic energies at the end. So we're going to have to disagree. All right, and so let's kind of dive into that a little deeper. We'll identify our system again, which is basically the same as before. In this case, though, we're going to use the energy principle to solve the same problem. We're going to assume pretty much the same things, but we are also going to assume that each disk's mass remains constant, so the rest energy will not change, and so on and so forth. But we're going to get into solving the problem. This time we're going to do it with energy. So we got this energy principle. The change in energy of the system is coming from any heat plus work, right? And we have the net work is any internal forces, work done from internal forces, plus work from surroundings. And that's the change in kinetic energy, which is basically final minus initial kinetic energy. So that's the work kinetic energy theorem. So that's the idea we're going to use here. We're also going to use this idea that work is basically force times distance times the cosine of the angle between them, so force times displacement. And we are then going to say, okay, well, in this case we don't have heat, so don't worry about that. We also don't have any internal forces, so don't worry about that. We also don't have any internal kinetic energy. I should say initial kinetic energy, so don't worry about the initial kinetic energy. It's not moving initially. And so what we'll then do is say, okay, well, work from the surroundings is equal basically then to my kinetic energy final. And so whatever work, whatever energy is added here must equal the final kinetic energy, because you didn't have any initial kinetic energy. And all of a sudden you ended up with some, right? So it had to have some more. That force was doing work. It was adding whatever final amount of kinetic energy you have. And so what we can do is plug in, okay, well, force times the distance there, L, FL, cosine of 0 degrees, because the force is in the same direction as the displacement, so cosine of 0 is just 1, is going to be equal to 1/2 mvf squared. We're then going to solve for VF, and we get the same expression as we did before. And so for the lesser mass, we are going to have, it's going to be traveling faster, but it's the same expression as before, just solved in a different way with the new principle. And so this is kind of transitioning, remember, to the energy principle from the momentum principle. It's just a different lens through which you can view this problem. And then we have the bigger mass, which is moving slower, right? And so hopefully this problem gives you an idea of how you can look at a given situation through the lens of the momentum principle with forces and time and like kinematic equations and things like that. Or we can take a different approach and look at energy and how energy is flowing into and out of the system through work and heat. And so it's just a completely new way of looking at it, but it's equivalent, right? So a lot of times you can solve the problem in either way and you get the same answer. And so hopefully that makes sense now, why we're moving into this whole different new principle. And we'll have some more videos coming up with the energy principle. So we'll see you next time.